Confidence intervals are the most commonly used statistical tool to express the uncertainty of estimates. Yet deceptively, they do not actually show the level of confidence that we have about a particular estimate, nor do they have a certain probability of containing the true value. So what do confidence intervals show? And if it is so complicated, why are they still so popular? That is what I want to show in this video. Suppose there's a clinical trial on a new cancer medicine. Measurements are taken before and after treatment, and the researchers will report some average decrease in tumor size. Now, the average change in tumor size of the patients that participate is of course important. But far more important is the potential average change in the thousands, perhaps millions of other people that might use this medicine after our study. It is this far larger group, the population of all cancer patients, that we try to generalize our conclusions to. And it is this theoretical value in the population that we're trying to estimate. There are many names for such a value, including true value, population value, or parameter. With a sample, like a single clinical trial, we can obtain an estimate of the parameter, but not the actual parameter itself, because we didn't measure the entire population, only this small subset of it. The question then is, how far is our estimate from the true population value? How good is this estimate? This is the motivation to compute a range instead of only a point estimate, to have some representation of the uncertainty of a sample estimate. And that brings us to confidence intervals. For the mean, here is one way to compute it. We take our mean and we add or subtract a measure of uncertainty called the standard error. We scale that, how much uncertainty we add, according to what level of confidence we want. A 50% confidence interval then looks like this. A 95% interval like this. And a 99% confidence interval looks like this. If you wanted to go all the way to 100% confidence, the interval would be infinitely wide. Now we're almost ready to see what exactly a confidence interval tells you. We just have to go through one more thought experiment. Suppose we would repeat this, the entire clinical trial, recruit 50 new patients, administer the same medicine, again measure all tumor sizes, estimate the mean, and construct another confidence interval. And then we do it again, and again, say 100 times. 100 repeated experiments, each with different patients, different means, and therefore each with its own slightly different confidence interval. Now we are finally ready for the big reveal. 95% confidence intervals have the property that at least 95% of the time they contain the true parameter. 95% of all hypothetical experiments that we could do would yield a 95% interval that contains the true value. Similarly, 99% confidence intervals contain the true value at least 99% of the time. This property holds for all levels of confidence. For example, 50% confidence intervals contain it at least 50% of the time. This, and only this, is what it means to have a certain level of confidence. And this thought experiment of repeating something a large number of times and then being able to say something about what would happen in theory in the long run is what we call frequentist statistics. But we didn't do our experiment 100 times. We did it once. And unfortunately, that brings us to the unintuitive part of frequentist confidence intervals. You can make no statements of probability about any individual interval. Your one experiment, your one interval, it either contains the parameter or not. But it is no longer a matter of probability. It is therefore incorrect to say that this one interval has a 95% chance to contain the true value. Only that the entire procedure we use to make these intervals is known to contain the right value in 95% of all hypothetical experiments. If you don't understand this difference, you're not alone. The definition of confidence intervals has confused experts and laypersons alike for almost 100 years now, since its inception in 1937 by Jerzy Neyman. To this day, Even many experienced scientists mistake confidence for precision, probability, or likelihood. But none of these interpretations are correct. To hopefully provide some intuition as to why, I'm going to summarize the arguments made in a highly cited paper on this subject called The Fallacy of Placing Confidence in Confidence Intervals. The reason, as demonstrated in the paper, is that there are different, all valid ways to construct confidence intervals. There isn't a single formula or procedure to do it. There are in fact many ways you can compute confidence intervals. They all result in different lengths, and yet they all have this same property of containing the true value x% at a time. And therein lies the fundamental confidence fallacy. If there are two such intervals, one narrow, one wider, then obviously they cannot both have a 95% chance to contain the true value. Now, you might be thinking, that doesn't make any sense. Clearly there must be one correct way to compute the interval, and the others are just wrong. But in their paper, Mori and his colleagues show 5 different valid procedures, all of which have the long-run property of being right x% at a time. I'm going to simplify their example a little bit further and just show you 2 procedures. In the example, there is a submarine which has gone missing, and a rescue team wants to know how confident they can be that if they lower their rescue line, it'll be close to the hatch. The submarine is exactly 10 meters long, and the hatch is precisely in the middle. Now here's the catch. The rescue team cannot actually see the submarine. All they see is 2 distinctive bubbles arising at the surface. The bubbles could come from anywhere along the length of the submarine, with equal probability. Wait, is that a realistic assumption? No, but this is just an example, so bear with me. Also, for simplicity, let's completely disregard common sense and assume the submarine is not moving in any direction and the bubbles can only move directly upwards. How could we construct a confidence interval for this problem? I'll show you 2 ways you could do so. I'm going to explain how they work, but only to show you there are no stupid metrics or paradoxes involved. Both procedures yield valid confidence intervals. If you'll take my word for it and you don't care about the math involved, feel free to skip to the next section. The first procedure works as follows. If the bubbles arise anywhere along the length of the submarine with equal probability, then for a given bubble, there's a 50% chance of being on the left and a 50% chance being on the right. That means there's a 25% chance that both bubbles are on the left and also a 25% chance that both bubbles are on the right. We're almost there because this leaves a 50% chance that one bubble is on one side and the other bubble is on the other side. In other words, 50% of the time, the hatch must be in between the 2 bubbles. And there's our first confidence procedure. A 50% confidence interval can be constructed as simply the range between the 2 bubbles. This interval will contain the hatch 50% of the time. The second procedure works not with the bubbles directly, but the average location of the 2 bubbles. The reason this works is because if all bubble locations are equally likely, then the mean of all possible bubble locations is the middle, where the hatch is. So confidence interval for the mean is a confidence interval for the hatch location. For our bubbles, this turns out to follow a triangular distribution. Let me quickly show you why. A fair 6-sided die has equal probability of each outcome. But if you roll 2 pairs of dice, there's only one way to roll a total of 2, but there are multiple ways to roll 3, 4, or higher. Once we get past 7, there are fewer ways to obtain a result, until we get to the largest possible roll of 12, which is only possible if both dice end up 6. This forms a probability distribution for each possible combination in the shape of a triangle. If you want the mean instead of the sum, just divide all outcomes by 2 and you still have this same triangular shape. It turns out this is true for all sums of 2 events with equal probability of the outcome. For example, this is what it looks like when you roll 2 20-sided dice. One way to roll 2, 2 ways to roll 3, etc. all the way up till 21, after which there are fewer possible combinations. Our bubbles do not have a finite number of possible outcomes, but you could imagine that if you just keep increasing the number of faces on the die, you will eventually end up with a perfect triangle. This then is the probability distribution of the sum of our two bubbles. And for the mean of our two bubbles, just divide by 2. And there we have the second way to construct a 50% confidence interval. If we simply take the center 50% of this probability distribution and add that to our observed mean bubble location, then 50% of the time, this interval must contain the hedge. If you're more easily convinced by actually observing things, you could simulate this experiment. Generate 2 random bubbles, compute the confidence interval with method 1, compute the confidence interval with method 2, and write down whether they include the hedge location. In this case, both of them do. Great, let's try again. Now the first one does, but the second one doesn't. To see if these intervals are indeed 50% confidence intervals, let's do this 1,000 times and see the result. If you want to give this a try yourself in R or in Python, I've added the code used to simulate this in the description below. As we get to 1,000 simulations, you can see that these are both really close to 50%. You can increase the number of simulations to 10 or 100,000 and get even closer. But the point is that these really are both valid 50% confidence intervals. So why is that a problem? Well, notice how sometimes one interval is completely covered by the other. If this bigger interval has a 50% chance to contain the true parameter, then it can't be that this narrower interval also has a 50% chance. And that is the fundamental confidence fallacy. A given confidence interval does not have a certain probability to include the true parameter, nor does it indicate precision nor likelihood. Counterintuitive as it is, you simply cannot attribute a probability of correctness to a single confidence interval. This 50%, it is a statement about a large set of confidence intervals, not about the probability of this one interval. Another way to think about this is that this 50% says something about the procedure used to make these intervals, but not about the intervals themselves. If you do want to make a statement of probability about a single interval, that is possible, but what you need is called a credible interval, which requires a different kind of analysis called Bayesian statistics. In Bayesian statistics, you assign a prior probability to the outcome, and then you update your prior belief using the data you have, resulting in a posterior probability distribution. For the submarine example, the authors suggest this as a Bayesian 50% credible interval. Contrary to everything I just told you, this Bayesian credible interval has the simple interpretation that, given the choice of prior, there's a 50% chance it contains the true parameter. In absence of further information, the prior used here is called a non-informative prior, which assigns equal probability to each possible value of the mean before seeing the data. Great, so we just get rid of confidence intervals and teach everyone Bayesian statistics, right? Well, that is pretty much what the authors of this paper call for in the conclusion, but this is where our opinions strongly diverge. Many statisticians, myself included, are strong advocates of Bayesian statistics, but it is not without drawbacks. Often, this posterior distribution is not actually something you can calculate. It involves integrating over all possible choices of parameters, which for many real-life applications is what we call intractable. So what Bayesians use instead are tricks to sample proportionally from the posterior without knowing the actual posterior. The idea being that if you have enough such samples, you have a decent idea of what the true posterior looks like. This is a very elegant way to do statistics, with simple, straightforward interpretation of intervals. But there are good reasons almost every statistics course starts with frequentist methods and not Bayesian. First, Bayesian statistics requires quite a bit more understanding of the underlying mathematics, probability distributions, and methods for sampling from the posterior. Second, Bayesian analyses usually take several orders of magnitude more computation time because of this sampling from the posterior trick. And third, perhaps most damning, unless you have strong prior beliefs or very small data sets, for many of the methods you will learn in a typical applied statistics course, frequentist confidence intervals often don't differ much from Bayesian credible intervals. Now, these first 2 points are well known and not really contested by anyone, but the third claim requires a bit more substantiation. Which brings me to the last part of this video, where I want to place the submarine example into context and look at some real data sets instead to see what different intervals actually look like. Let's start with the elephant in the room. Nobody does analysis like this. Just because these are both technically valid ways to construct a confidence interval does not mean that anyone would use this to make a decision. For example, why do we assume bubbles arising from anywhere with equal probability? A submarine clearly has a shape that would make bubbles more prone to form at certain areas, like edges, windows, the propeller. And perhaps more importantly, can we just wait for more than 2 bubbles? Now, to his credit, the author has elaborated online that the example is merely meant to demonstrate that confidence intervals do not, in general, have the properties often associated with them. But if I'm perfectly honest, even though I really like this paper, this example is a straw man. It is only with carefully constructed examples like these that frequentist methods look absurd, and that Bayesian statistics looks like the only sensible answer. To be clear, Bayesian statistics can strongly differ from frequentist methods when you have very small datasets, strong prior beliefs, or a combination of both. But just to provide a more realistic comparison, let me also show you some analyses on actual data using various regression models you might actually learn about in an applied statistics course. You don't have to understand the models used here to understand the comparison. All I want to show is just how close frequentist confidence intervals tend to be to Bayesian credible intervals, with at least a couple dozen observations and no strong prior beliefs. I chose these datasets because they're freely available and they allow me to show you a range of possible models you might actually use. But it is of course possible that in your data there is a large difference between either of the 2 intervals. I've added the analysis used here as a Cordo Markdown file, which you can download using the link in the description. So let's get to it. In the first example, I used ordinary linear regression to see how different demographic variables affect median housing price in Boston. Shown on the y-axis are the different contributing factors, like crime rate and the average number of rooms per dwelling, and on the x-axis we see the values for the corresponding confidence intervals. At the top we have the intercept, and below that we see, for example, that apparently crime rates don't have much of an effect, whereas unsurprisingly, the number of rooms correlates quite strongly with housing prices. After fitting this model, I ran the same linear model using the Bayesian R-stan-arm package and computed Bayesian credible intervals. These were the results. Practically identical. Now, surely the problem is that I simply went with the package's default priors, right? So let's try something else. Here's the same model using a different choice of prior. Still not much of a practical difference. Maybe the problem is ordinary linear regression? Here's a slightly more complex model called a gamma GLM. In this dataset, the researchers wanted to see how levels of a certain protein in urine changes with age. Again, on the y-axis we see the estimated parameters, in this case an intercept and a slope for age, and on the x-axis the resulting confidence intervals. Afterwards, I fitted the same model using Bayesian methods and computed credible intervals. Once again, practically identical. Alright, now a little faster. Here's an example of count regression, using a Poisson distribution to model the number of warp breaks in wool. Again as good as identical. Maybe count regression allowing excess variance? Oh wow, finally, a meaningful difference. For this model you can see that all confidence intervals are too narrow, which means that you would underestimate the uncertainty. What about logistic regression? And we're back to practically identical. What about a mixed model? Same story once again. Out of all examples, only once were the confidence intervals too optimistic, and even then they weren't that different. So is that it then? Is there no point in bothering with Bayesian statistics? Well, not quite. First off, I did not invest a lot of time in picking sensible prior choices. If you do have strong prior information, like a previous study, the intervals will diverge. Second, if we want to see a difference, all we need to do is work with smaller datasets so that the effect of the prior is more pronounced. That I can easily demonstrate. In the next comparisons, I randomly removed most of the observations and reran all the examples. You can find the details in the Corto file in the description, but here are the results. For the Boston housing price data, after removing 90% of all observations, there still wasn't much of a difference. But the gamma GLM shows a clear underestimation of the uncertainty when using confidence intervals. The count regression with a Poisson distribution was still indiscernible, but the negative binomial, the one with excess variance, shows confidence intervals more than twice as narrow as their Bayesian counterparts. In the logistic regression example, the difference was still subtle, and in the mixed model example, we now also see a clear underestimation of the uncertainty. In summary then, if you have small data sets or strong prior information, then frequentist intervals tend to underestimate the uncertainty and are potentially off entirely. But if you have a decent number of observations and are using one of these all too common regression models, I hope we can agree that confidence intervals aren't nearly as ridiculous as the submarine example would suggest. The takeaway message here is to be careful how you phrase your results. Precise wording is not just scientists being pedantic, but it avoids further propagation of misunderstandings. Imagine if we all just used the simple but wrong interpretation of confidence intervals. If someone were to use this 95% in any further calculations, under the false impression that it is a probability, it could be off by an unknown, possibly very large amount. Think of the rate of serious side effects of a medicine, the probability of default of large loans, or the time until the next major earthquake. Underestimating uncertainty can be very dangerous. If you just want some indication of the precision of your estimates before moving on to the next problem, frequentist confidence intervals often give you very reasonable answers, and they're easier to use. And that is why, despite their unintuitive interpretation, and despite the fundamental confidence fallacy, the whole world, scientists included, still largely use confidence intervals. Convenience, pragmatism. And you should too. Just make sure you use the right wording for your conclusion. But if you really need an answer you can phrase in terms of probability, you need to use a Bayesian model with credible intervals. A confidence interval may or may not coincide with a Bayesian credible interval, but you have absolutely no guarantee that this is the case for your model and your data. So it is important to understand the difference between these two types of intervals and use the one which is appropriate for your research. That was a long explanation for a single concept, but this is typically one of those things I wish I understood better earlier. Most, if not all of you, will encounter confidence intervals later in life, regardless of your career choice. They're common in science, in business, even in the news. That is why I wanted to make this video. I tried to keep it at least somewhat short, but if you do have any remaining questions, I'd be happy to answer them in the comments. Thank you for watching.